Hello everybody, welcome to my third video about this subject, looking at Black Scholes formula from different perspectives and doing some simulation about with Monte Carlo simulation about the dynamic hedging and what kind of conclusions we can derive from this. And since it is my third video about this, I will try not to repeat myself what I said before, just to provide you with additional perspective or maybe relatively different conclusions. And I will also give you the possibility of playing with my Excel programs, so the Excel programs will be attached to this presentation. The most important thing is what I see from what I discovered in the last couple of months is that when I look at D1 and D2 as z-scores, I can analyze Black Scholes formula much better than before. And then also what I have to share with you, when you will do Monte Carlo simulation, we can't stop too early. We have to do a lot of simulation to come to the results which are reliable, which are replicable, and you come to always the same results. So in my previous simulations, I did not enough. I made around 50,000 simulations for each case, and I increased this as almost by factor 1,000, so 130 million simulations, and the results are a little bit different. You show most of this what I'm showing on this chart before in my previous presentations, but what I want to add here, when I take this part showing a binomial tree, and with help of the binomial tree you can also calculate not Black Scholes, by option premium, and with enough steps you have the same you have the same results as with the Black Scholes formula. Also, you could calculate a mean of the tree of which you obtain when you calculate spot rates with help of binomial tree, and you see based on the same data as Black Scholes formula, I obtain the mean of the population, which is the same when we have the precision of only 4 digits after the comma, after the point, as with the Black Scholes formula. So Black Scholes formula brings us this is the mean according to the Black Scholes formula, which is used in the Black Scholes model, and this is mean according to the binomial tree. So they are very similar. And please don't forget, when you use z-scores, or you have the table for z-scores, on the z-scores normally show the probability which are less than z. So this is the area less than z. But when we calculate call options, what do we need? We need the probability higher than strike price, so it is the bigger than z. So we are looking for this area. So z-score, the other perspective, you can look at the z-score as the cumulative, but you can also look at the z-score, what is the probability, how far you are from the mean, away from the mean. So up to 1 standard deviation from the mean, you have 34% plus 30, so 68%. If something happens between 1 plus 1 minus standard deviation. But for the purpose of Black Scholes model, we need this cumulative probability. It is the above we have the Black Scholes formula. Black Scholes formula tells us that in order to calculate call premium, you take strike price, discounted strike price, not strike price, the spot price, discounted spot price times volatility according to D1 minus strike price or correctly discounted strike price times the probability according to D2. And for D1 or D2, Black Scholes model use these formulas after discovering or realizing that this is nothing else like the D1 or D2 has been z-scores. I could transform this D1 or D2 into mean 1 and mean 2 and calculate probability using log normal log distribution function from Excel or Google Sheets, and you can calculate the probability accordingly. Whether you do this way or the other way, the results are always the same. So you probably will do what you normally did before, but what is very important, I see, not how you calculate, but how you realize what ND1 and ND2 mean. And in my view, this the ND1 and ND2 are two probabilities or two distributions with the same volatility but different means. Understanding the Black Scholes formula in this way, we can use the graphic where we calculate the blue, that is ND1 probability, and ND2, and in orange is ND2 probability. And when we know that the mean of ND1 is higher than mean 2, so with a higher mean, we have the strike price, and you see this in the case of ND1, strike price is below the mean, so the probability that something happens after the mean or as correctly in the Black Scholes formulation, that the prices are higher than strike price, the probability according to ND1 is more than 50% because it's lower than the mean. Exactly, in this case is 56%, but according to ND2, where mean is lower, so the probability is the after the mean, and so it must be less than 50%, and in this case is 41%. So we have ND1 and ND2 different probabilities because their distribution has different means. So I think this is the correct explanation. And when you look on the probability on this probability function when you change some parameters. In this case, I changed the volatility. Volatility is increased from 40 to 60%. You see that both functions are wider. However, the impact on the blue is a little bit higher than on the other one. You see that we had the probability of 56 increase to 61, and the probability of ND2 goes down from 31 to 37, and correspondingly our according to the formula, when we multiply the spot price with the probability, which is now higher, so we can gain more, and strike price multiplied with its volatility, where we represent the costs, is lower. So the costs are lower, possible gain is higher. What's happened to the call premium? The call premium must go up. So you can see this out of this graphics. We can also see what happened when we change another parameter. We change, for example, interest from 3% to 10%. So what happens to the to our probability functions? They move, they change position, they move to the right. So you see now we have ND1 was 56, is going up to 60, almost 64, and ND2 is going from 41 to 48, and correspondingly the call premium as the net effect is also going up, so increases to $4.4 for each call premium. We can also change and make the different change. We could say, okay, we have increased the price of the option to $4.4 through the increase of the interest from 3% to 10%, but we could leave the interest at 3%, but instead increase the spot price to 26.277, and what we obtain almost the same increase in the call premium from 4.4 to 4.436, so almost the same. You see, you can see how different parameters, how they impact the cost side, and how they impact the cost side, I mean ND2 in this probability, and the possible potential gain resulting which represents the probability for ND1, and you can better see how option premiums will react to the changes in individual parameters. So I try to show this with help of the graphic, that increasing the volatility leads to normal distribution curves being wider, but the impact is slightly different on ND1 and ND2. We have also seen impact of increase of the interest rates from 3% to 10% as per mean formula. Per mean formula, this means the difference of 7% is added and means increase in both distributions and move to the right. The probability that spot prices will be higher when strike prices increases, and correspondingly the call premium is higher. When you check the formulas for mean 1 and mean 2, you notice that dividends of foreign interest will be subtracted. So if we increase the dividends, the distribution curves move to the left. The probability that spot prices will be higher when strike prices goes down and call premium is lower. We could achieve the same movements of curves moving to the left or right by changing interest or dividends, but also by changing the spot price. And we showed this, that the increase of the spot price from 25 to 27.277 is similar to increase in interest rate from 3 to 10%. When you interpret ND1 and ND2 as two different distributions, you can graphically analyze the impact of each variable in the Black Scholes equation, and this is more meaningful than saying that one is risk adjusted and the other is contingent probability. Now back to the second part of my presentation. Monte Carlo Simulation and hedging ratio. We will check with the Monte Carlo simulation how good ND1 as hedging ratio performs and compare this with the hedging ratio as per ND2. It is very interesting that mean 2 is the true mean of the population as checked using binomial trees, but hedging according to ND2 is not quite successful. Current simulation with 130 million simulations per each scenario supports findings showed in the previous presentation as far as dynamic hedging is very good risk reduction instrument. Hedging according to ND1 does not generate best hedging results in all circumstances. When actual volatility is higher than assumed volatility, dynamic hedging does not offer sufficient protection. The idea of dynamic delta hedging requires a continuous rebalancing of portfolio. Dynamic delta hedging is applied by market makers to protect their position. Hedge fund managers may also apply dynamic hedging to protect their position. However, dynamic hedging is not the right strategy for corporate treasurers. You cannot accept for corporate treasury that they will be on the market continuously and change their position every 10 minutes according to the change of the market prices. It's not what the corporate treasury is for. So, in my previous presentation of Monte Carlo simulation, I based this conclusions based on 115,000 iterations for each scenario, altogether 4 million simulations. The current presentation is based on 180 million iterations for each scenario. How I come to this 180 millions. The year is based on 360 days with help of Excel data table function. I execute this for not for 500 or 380 years, but for 1000 years. And then applying VBA, I repeat the process 500 times. So altogether I have 180 million. And I average this, and these results are in principle very stable. They are the same. If I repeat this simulation again and again, I am not obtaining different results. This is my model. The model the same as in the previous presentation. And I didn't change anything. The same is that in the previous presentation I stopped here. I obtained the average with help from the I obtained the table with the help of the data table function, and the average for this 500 simulation was obtained as the average. Now I create here 1000 table with 1000 repetitions or simulations for 1000 years, and then with help of VBA I take this average and I create new column where this average will be added or not added but save again and again 500 times, and then I can create the average in the column in the row 6. So this is obtained by average results which are stable. So if I do it again, I always have the same results. Now, out of the simulations, if you want, you can read here slowly. So describes in principle my table here, which I created with the simulation. So we have the simulation at 180 millions. At first start we have the at the money simulation, in the money, out of the money, and I change volatility. And on the left side is for ND1 and for ND2. So start with ND1. We have volatility of 40%. We have the different assumption about the return. spot price remains the same, we set the money, and then we have the results of simulation. So according to Black Scholes, I should obtain in this situation the premium of 371. According to my dynamic hedging, this almost didn't change, you see. Less than 4 was 1 cent, less than 1 cent, less than 1 cent difference. So in percent, the difference is 0.11%, 0.14%, and so on. The difference is slightly higher when you use ND2, but still I would say if I wouldn't have the ND1, I would use ND2, because ND2 is also very relatively good. The worst difference is 11% under the different scenarios. So you see we have 40% volatility, always the same. Return, I change return from 27 minus 9, 20%, and now you see the results of simulation. They differ from 371 by minus 42 cents. They differ by minus 11 cents. Here they differ by additional 15 cents, and here additional 35 cents in addition to obtain premium as per Black Scholes. In principle, very similar results to my previous presentations. That the results using ND1 is you are hedged extremely close to the Black Scholes model. If you use ND2, you can achieve more or less, but you are still pretty good hedged. Now what happens if when we are going the money, so spot price we change to 30. Also here ND1 results of simulation almost a little bit better than call premium, but almost the same. Again, ND2 is volatile, so the hedging according to ND2 can bring you a little bit worse, but also a little bit better results when prices in the future go down. What happens when we are going now out of the money? Still, out of the money is also very good protected. It doesn't matter whether we are out, in, or out of the money. Hedging, when the volatility stays as in the Black Scholes model assumed, we are very good protected with the dynamic hedging. You see, less than 1 cent, where the return is 7 or return is minus 9%. In case of ND2, pretty good hedged, but not as good as with ND1. With the positive return, we are slightly 11 cents negative with 9%. Okay, we have here 10% positive, so it's more volatile, and with minus 20%, we almost obtain 30, so 27 cents more than according to Black Scholes. So altogether we have 148 plus 0.271. Now, in the real life, volatility is not constant. Volatility can change. So when the volatility changes, what happens to our hedging results? When the volatility goes down, we get substantially more. We can get up to 371 Black Scholes plus additional $2. But when the volatility go up from 40 to 60 by 50%, we will be penalized. We get half of our premium, or more than half of our premium is gone, because dynamic hedging created additional costs, which were by far not compensated by premium. And when when volatility is even substantially higher, increases by 100% from 40 to 80%, then the premium is in principle eaten by costs of dynamic hedging. So we have loss premium and we have additional loss of 384.6 more than $3. And if we change, when we reduce return, the loss is slightly smaller, but still we have eaten totally the premium which we obtained, or almost, because it's 371 loss. So the premium is offset by the loss which we realize through through change of the volatility and change of negative return. What happens to when we hedge with ND2? Yeah, you see here the interesting results that when we have the higher volatility, of course, we also make the losses with ND2 because we assume volatility of 40%. Now volatility is 80%. But if we have also negative return, the losses are smaller. So we reduce the losses partly, or still with when the market go down by 35%, we would not totally, but not the total premium will be eaten. We still would have $1 left because we would realize that $2.95 loss, but we got $371 premium. So this is my description about this many billions of simulations and what came out of this. Conclusions. Dynamic hedging success of Black Scholes model hinges on volatility. Yeah. And volatility stays as we assume. We can achieve the same with the dynamic hedging. In the model, the volatility remains constant. Under assumption, dynamic hedging according to ND1 shows perfect results. I can say that the perfect results with ND1. ND2 is not as good, but as long volatility stays as assumed, ND1 provides us perfect hedging, whether it is in the money, out of the money, or at the money option. In the practice, volatility is not constant and requires consideration. Vega hedging might be a potential remedy. If we knew that a particular asset will perform negatively in the future, we can contemplate applying delta hedging according to ND2. But in my view, this would be speculation rather than hedging. Thank you for listening. I hope you learned something and you like it. Thank you very much.